like to thank the organizers for what's really been a lovely conference so far. It's a great pleasure to be here. And I would like to thank the audience for hanging in there, even though the Germany-USA game is starting at this moment. So we'll try and make this short and sweet. But thank you very much for your attention. So I'm going to be talking today about two different projects which have some overlapping goals. The first one is work that is done in collaboration with Washington Taylor at MIT. And appeared fairly recently, a couple of months ago. And the other is an ongoing project with Jonathan Heckman and Sheldon Katz. Also, there's a recent paper on this and more to come soon. So to start, sorry, don't seem to be able to go forward. There we go. So to start, I want to start with some general motivation for the questions that we're tackling. This is going to be, I want a very general bit of motivation first, and I can't quite do what I want to do yet, so I'm going to then tell you about what we did instead. So here's a thing that we would love to be able to do. There's been a lot of recent work classifying which effective theories can rise from string compactifications in various dimensions with various amounts of supersymmetry. Suppose that I'm interested in four-dimensional effective theories. Let's say n equals 1, because I'm interested in perhaps some very specific effective theories. I would love to understand, in general, the Venn diagram that I've shown here. I would love to understand whether string compactifications sweep out all effective theories that I could get n equals 1 theories in 4 dimensions, whether it's only a subset, what characterizes that subset, and perhaps I'm interested in some particular field theories in 4 dimensions. Perhaps I'm interested in questions in string phenomenology, like building effective theories like the standard model or cosmology. Unfortunately, of course, this is a really difficult question for a lot of reasons. The primary one being that in the process of string compactification, we replace the rules of building effective field theories with the question of what is the underlying geometry of the string reduction on this background. And the problem is that this brings us up against a lot of very difficult questions that in general we don't know how to answer. So although I know how to write down a consistent quantum field theory that looks like the standard model, answering the question, does that come from a particular string compactification? Is there a geometry which gives me exactly the spectra and symmetries that I'm interested in? That's a harder question to answer. So because this question is a little bit too hard to tackle in general, I want to pick a corner of string compactifications where I have a lot of tools and I have a shot at taking a more systematic approach to this question. So specifically, I want to combine a lot of recent advances and tools in two different areas of n equals 1 string theory. I want to consider four-dimensional compactifications in which heterotic string theory and F theory produce the same four-dimensional effective theories. The reasons for this is basically that where I have a very large toolkit and I can understand tricky aspects of the geometry through multiple windows, I may be able to get further and in a more systematic manner than I could otherwise. So the goal is going to be to try and systematically construct such vacua, try to understand how to filter the effective theories through the background of these geometries. So what do very simple things about the geometry, for example, its topology, tell you about which effective theories you can get, and perhaps learn something about how to engineer theories that I'm interested in the process. So let me just remind you in one slide where these two types of string compactifications give you the same effective physics. Heterotic string theory, I'm going to be focusing on the E8 cross E8 heterotic string, though there's also a story for SO32. E8 cross E8 heterotic string theory, compactified on an elliptically fibered Calabi-Yau n-fold, is dual to F theory compactified on a K3 fibered n+1 fold, Calabi-Yau n+1 fold, where the base manifold that I'm going to choose for these fibrations is the same across both halves of the geometric pair. So this, the simple way to think about this is in Vafa's original construction of F theory, he made the observation in 8 dimensions that the E8 cross E8 heterotic string on T2 gave the same 8-dimensional effective physics as F theory compactified on an elliptically fibered K3 manifold. Heterotic F theory duality in all lower dimensions just takes this duality and fibers it over some shared base. Since I'm interested in 4-dimensional compactifications, I'm going to be interested in a complex 2-dimensional base that is common across both pairs of this geometry. Now, I should say up front that this is a subject with a 20-year-old history. A lot is understood, which is why it's an attractive area to try and push forward in a systematic way. There's a very rich history and many wonderful tools. This is a very incomplete list of people who've done beautiful things on this subject. So if I have not cited the complete literature here, I apologize in advance. But there's a lot of tools. Another reason that we might be interested in this particular corner of string compactifications is a nice observation, which is in the region of string geometries and string effective theories, where these two theories are giving me the same physics, there is in fact a finite number of effective theories and effective geometries, geometries and effective theories that I might be interested in. And that's a non-trivial fact. So let's think about this for just a second. We don't know, let's say I'm interested in heterotic compactifications for a minute. I don't know whether the number of distinct topological types of Calabi-Yau threefolds is even finite. However, if I impose an elliptic fibration such that this duality holds, I'm in better shape. It is actually known that the number of elliptically fibered threefolds is finite. This was demonstrated by Mark Gross. And indeed, in the ways that we know how to build elliptically fibered, just know how to build Calabi-Yau threefolds in general, it appears that elliptically fibered ones are actually extremal in known data sets. So what do I mean by that? If we look at here, this is the famous Kreutzer-Skarke data set of about 500 million toric polytopes, which lead to Calabi-Yau threefolds as hypersurfaces in these toric varieties. If you look at this data set of Hodge numbers, which unfortunately I cut off my axes here, but if you haven't seen this before, this is the sum of the Hodge numbers, H11 plus H21 and the difference. If you look at these plot of Hodge numbers, it's an interesting fact that in fact the vast majority of this data set is elliptically fibered. This can be quantified for other known data sets of Calabi-Yaus. For example, the number of complete intersections in ordinary products of projective space is about 99.6% of all known manifolds are elliptically fibered. Indeed, it's actually been demonstrated recently by both Waddy Taylor and Philip Candelis that in the Kreutzer-Skarke data set, actually all of these extremal bounding sets of Hodge numbers in the known Calabi-Yaus, all of these manifolds are elliptically fibered, and in fact, known examples of elliptic fibrations actually saturate the maximal possible Hodge numbers that can arise for elliptically fibered threefolds. There's been interesting work from other points of view, from Oguri and Keller, that found that in fact, these numbers that appear at the very extremal ends of this diagram, like Hodge numbers 11 and 492, these may be significant for other reasons. These are all just hints, but what I'm trying to point out with this illustration is that I'm going to consider elliptically fibered manifolds because they're finite, but they are in fact actually very dense within the known manifolds that we have to work with so far, and we may be able to learn things that we can extrapolate more generally. So let's stick with this argument about finiteness for a second. Let's imagine that I'm interested in heterotic compactifications. I'm going to begin with a finite set of Calabi-Yau threefolds. Now, in the E8 cross E8 heterotic string, I also have to parameterize the E8 cross E8 gauge fields, and specifically the vevs of those gauge fields in the extra dimensions, the Calabi-Yau directions. Mathematically, that's parameterized by vector bundles. I've got two of them here, one for each E8, which live over the Calabi-Yau threefold. So what about those? Are there a finite number of configurations for these gauge fields? Well, the question really is about the moduli space of such stable bundles that satisfy the conditions for n equals 1 supersymmetry. A nice observation is that this, in fact, has only finitely many components for fixed topology. So what do I know about the topology? I know that the rank of these bundles over the Calabi-Yau has to be such that I can embed its structure group H inside E8, by definition. I'm interested in having spinors in my 4D theory. This gives me a condition on the first Chern class of the vector bundles. This is really 0 mod 2, and in the irreducible case, honestly 0. There's also a famous anomaly cancellation condition which relates the topology of the vector bundles over the Calabi-Yau with that of the holomorphic tangent bundle of the Calabi-Yau itself. This provides an effective bound on the second Chern class of my manifold, of my bundle in terms of the manifold. And there's some recent and very lovely work in mathematics literature which has shown that for fixed C2 of a vector bundle that is stable, there are in fact only finitely many values of C3 which are compatible with, I've written this here as n equals 1 supersymmetry, or mathematically the slope polystability of the vector bundles. Okay, so what's the punchline? At least in this corner of heterotic string compactifications, I am guaranteed that there is in principle a finite number of effective theories, a finite number of geometries that I could try and construct. Unfortunately, these bounds for both the manifolds and the bundles as I've laid them out are non-constructive. I don't necessarily know how to write all of them down now, but I know that it is at least a good starting point. So I'm going to try and get as far as I can towards systematically writing stuff down. So what is the plan? In recent work with Waddy Taylor, what we tried to do was systematically study the general properties and constraints of the effective theories for this class of string compactifications. We wanted to develop a general formalism where we wanted to ask what are necessary and sufficient conditions for building good geometries of the type that I just described. So for a smooth Calabi-Yau threefold, the geometry is really characterized by this shared base manifold B2, which appears on both sides of the geometry. It is known that this must be a generalized Del Pezzo surface if X3 is smooth. There are a finite number of topological types of these. So we wanted to build an algorithm to construct all possible B3s, which are going to appear as the base of the elliptically fibered fourfold, that are non-degenerate P1 fibrations over that B2. Specifically, to explore and test this structure, we wanted to build a data set to play with. Happily, such a data set of bases is readily available. Recently, Morrison and Taylor classified about 62,000 toric surfaces that I could use for this project. Unfortunately, because I'm interested in smooth Calabi-Yau threefolds, this restricts me right away very rapidly. Of that 62,000, only 16 of these will lead to smooth Calabi-Yau threefolds, so I'm going to start with that. And as I'll demonstrate in a minute, that leads me to an example set of about 5,000 fourfolds. A few technical caveats. I'm going to, by hand, construct these manifolds in a specific way. I'm going to guarantee that all fibrations have a section. And I'm constructing the elliptic fibration and the K3 fibration of the fourfold in such a way that the base is a P1 bundle rather than a P1 fibration over this base manifold. I should say here that my goal is to do this in complete generality. I'm just using some toric examples as illustrations, but the techniques that I'm about to talk about will be completely general. Okay, so just to remind ourselves a little bit about what, when you have elliptically fibered manifolds, what are the ingredients in the geometry and what are you trying to identify? One of the basic bits of the heterotic F-theory dictionary that I'm going to care about is the ways that the degrees of freedom in the theory are going to map across this duality. So one that's going to be important to me is, in fact, that the complex structure moduli of an elliptically fibered Calabi-Yau fourfold Y4 have to be related to the degrees of freedom that describe those gauge fields, the bundle moduli space, on the heterotic side. So beginning with an elliptically fibered manifold in so-called Weierstrass form, this is a description of the elliptic fiber, where the coefficients of this polynomial that are describing an elliptic curve, f and g, are functions over the base manifold such that f and g are sections of these line bundles. So beginning with some description of an elliptically fibered manifold, what kind of comparison do I want to do? Well, in F-theory, I want to tune singularities, or perhaps they're there generically, into the elliptically fibered fourfold in ways that we've heard about a lot this week already. So for example, suppose that I have F-theory with an E7 singularity. Then the Weierstrass form takes a very particular, Weierstrass model takes a particular form, such that these polynomials f and g vanish to a particular order here in the polynomial coefficient z equals 0. In the neighborhood of the 7-brane, which is going to be parameterized by z equals 0, I can write this locally as something that looks like this guy in red here. Sorry, this is a little bit small. The normal directions to the 7-brane are parameterized by this form of the Weierstrass equation, and particularly these polynomials f3 and g5 describe the normal directions, locally the complex structure of that fourfold. On the heterotic side, this same data that appears in an elliptically fibered fourfold appears as a way to describe vector bundles in the heterotic geometry. There's a whole long and interesting story here to do with Fourier-Mackay transforms of vector bundles over elliptically fibered manifolds, but just to illustrate, in the case of an E7 singularity, the bundle in question would be an SU2 bundle over the Calabi-Yau threefold in the heterotic geometry. And that's going to be described by a polynomial equation of this type, where here this has two roots in the elliptic fibration of the heterotic threefold. These two roots correspond to restrictions of the rank 2 SU2 bundle to the elliptic fiber. The punchline here is that these degrees of freedom that appear in the Weierstrass form, so complex structure moduli of Y4, these get mapped into the degrees of freedom that describe the vector bundle on the heterotic side. So this dictionary, if you didn't follow the details of that, that's okay. This is just its illustration. When I start tuning the complex structure of a fourfold, that's going to have some consequence for heterotic gauge fields, and I need to understand what that is. So let's try and do this systematically, independent of any construction. I mentioned before that the shared ingredient here is the base manifold B2 across both sides of this pair. What I want to now do is systematically construct bundles and elliptically fibered fourfolds. So the idea is going to be that I want to choose topology of my bundles V1, B2, and that's going to correspond to building a P1 fibered base manifold B3 over some B2. I want to understand what are the rules for this and how I match these degrees of freedom. So starting on the heterotic side, I can expand the second Chern class of my bundle without loss of generality on an elliptically fibered manifold. I can expand that in such a way that I can break out one particular piece of this topology. Specifically, I can expand the second Chern class as some form here that I've called eta, wedged together with the dual of the 0 section of my elliptic fibration, plus some stuff that's pulled back from the base that I don't care about. When I look at what the anomaly cancellation condition that relates C2 of the holomorphic tangent bundle with C2 of my bundle, when I look at what that gives me, it relates this class eta, which is a 1-1 form over the base, to the geometry of the base itself, plus something that's called the twist. This is a 1-1 form on the base. On the F-theory side, building this B3 P1 fibration, I'm going to build this as a P1 bundle, which is a projectivization of two line bundles over the base B2. A simple adjunction formula gives me a formula for the topology of that base B3 in terms of, again, the shared base geometry B2 plus some stuff. Now, as you might suspect, the stuff in blue is in fact the same on both sides of the geometry. This was demonstrated in the stable degeneration limit by Friedman, Morgan, and Witten back in the very early days of heterotic F-theory duality, and demonstrated more recently just from an effective field theory argument using no geometry at all by Grimm and Taylor. So here's what I'm going to give you as input geometry. We're going to start building geometries. I'm going to tell you that I need to specify some piece of the topology of bundles on the heterotic side. This is going to give me the topology of a P1 fibered base on the F-theory side. And now to really enumerate things and start studying the effective theory, I have to decide how many different ways I can do this. So is there a finite number of B3s, respectively topology of bundles that I'm interested in? Can I solve them and enumerate them? So what is the restrictive feature? What prevents me from doing an infinite number of solutions of this type? Well, the real restrictive feature is, of course, n equals 1 supersymmetry. So in the heterotic side, this has a very simple form. This is just the condition that the Calabi-Yau threefold, the Calabi-Yau geometry is a Calabi-Yau threefold, and that the vector bundles in question satisfy the famous Hermitian-Yang-Mills equations written here. In F-theory, the condition that I really have to play with for supersymmetry I've inherited from M-theory, which is that the geometry that I'm compactifying F-theory on is a Calabi-Yau fourfold. Now, because I'm considering singular Calabi-Yau fourfolds in order to have non-trivial gauge symmetry, I need to ask exactly how singular I can be such that the resolution when I go to the M-theory limit returns me to a Calabi-Yau fourfold. Now, this is well known that, in fact, when I consider how singular the manifold can be, there are simple conditions on F, G, and the discriminant locus of that fibration that tell me exactly how singular I can get before I get in trouble. So specifically, I need the vanishing degrees of F, G, and delta as they appear in the Weierstrass form to be less than or equal to 4, 6, 12 on every divisor in the threefold base B3. Likewise, F and G cannot vanish to orders 4, 6, or greater on any curve, and there's also some conditions on codimension 3 singularities, which I didn't have time to write here. It turns out that when you compare what these two conditions on each side of the duality require for you, they produce exactly the same thing. Namely, that eta, remember, this is this guy in the heterotic geometry, piece of C2 built out of this twist T. This guy eta has to be an effective class in the base B2. Now, because this is appearing, eta has two different etas here that I'm interested in, one for each E8 bundle. And because this twist T in both cases has to produce an effective eta, this is bounding the twists from above and below. Okay, so that's one bit of ingredient. The other interesting thing is that by studying exactly how singular you can go on each divisor and each curve, you very rapidly discover that only certain divisors can carry singular fibers of an appropriate type without getting too singular again. Another condition that I'm interested in is where this class eta is what's called base point free. As a divisor class within my twofold base, this simply means that if I pick any point in the base, I can find an element of the linear system of eta that does not pass through that point. Simply a sort of a genericity condition on this class eta. This implies that if there for any effective curve of negative self-intersection, eta dotted into that curve has to be less than 0. Why is this interesting at all? Well, it starts to filter for you which possible symmetries are associated to which etas. As it turns out, for SUN structure group of my bundle, leading to symmetries like SU5, SO10, E6, E7 in 4 dimensions, the eta in question must satisfy this condition of base point freeness. In the presence of generalized Del Pezzo surfaces with curves of self-intersection -2, it turns out that you have a bit more freedom. So you can have a wider variety of structure groups. This seems like a pretty boring geometric statement. Let me try and make this more interesting for the actual 4D physics and see what we can do to systematically start filtering this type of information. So the sample question that I really want to answer now is a part of the effective theory. I want to say, given the topology that I've described so far, how does that topology constrain the 4D gauge symmetry? Phrased as terms of a mathematical question, which symmetry I can have in a heterotic compactification is related to which vector bundles can exist over the Calabi-Yau threefold. Now, of course, mathematically, this is a very difficult question. Understanding the moduli space of higher rank sheaves over a Calabi-Yau threefold is a hard thing for general topology. But this is the kind of question that I want to start attacking. So the first step is going to be, I want to consider all possible fourfolds with perturbative heterotic duals, and I want to see how to systematically constrain that moduli space of stable bundles. In order to fully do that, I'm going to have to add in g-flux on the fourfold to fully determine that moduli space. I'll get to that hopefully briefly at the end. But for starters, let's just look at what the manifolds themselves give. And as a test, here a description of the 5,000 manifolds that I've built to see what, in concrete examples, this actually looks like. So here are the 16 toric bases which lead to smooth threefolds. This is the number of possible B3s, i.e. the number of vector bundle pairs that I can build over each one. Okay, so in order to ask questions about 4D gauge symmetry, I want to be able to translate that into two geometric questions. If I start with some symmetry in 4 dimensions, two things could potentially happen to it in my 4-dimensional theory. I could Higgs the symmetry. It could be broken. So what does that mean in terms of the geometry? On the heterotic side, if I'm getting rid of symmetry, that means I'm carving out more of E8 with my vector bundle, right? I'm breaking more in the internal dimensions. So that means I have to be able to deform the vector bundle geometry into something bigger that takes up more of E8 in order to break 4-dimensional symmetry. So geometrically, this is a deformation problem of starting with the vector bundle plus some number of copies of a trivial bundle and deforming it into something indecomposable of higher rank. In the F-theory geometry, Higgsing a symmetry just means deforming the complex structure of the fourfold to smooth out the singularities. Okay? The other thing that I could do is I could try at special points in the moduli space to enhance the symmetry. So I want to grow more symmetry in my 4D physics. Again, this makes sense. In the heterotic geometry, this corresponds to ways to decompose the vector bundle into reducible pieces, leaving more of E8 unbroken. And in the F-theory geometry, this just means that I'm going to tune the complex structure moduli of the fourfold to produce more singular geometry and higher rank 4D physics. Okay, so with this very simple dictionary in mind, what can we start to see? One of the first things that you see for the data set that I just mentioned of the 5,000 manifolds we built is you can tabulate which symmetries are generic for all points in the complex structure moduli space of the fourfolds that you build. So if you look at this, in this table here, I have 2 columns with different symmetries. This is 1 for each E8. So a number here, the 2 dots, mean that I have 712 manifolds, thank you, with no symmetry at all in each piece. If I go all the way up to E8, I have 4 that have a forced E8, E8 over that fourfold. So just to say again, this is a question for generic symmetries. If the symmetry is generic, it means there's no moduli within the fourfold that could possibly be given a vev to break that symmetry. There's no deformation that will remove that symmetry from me. What does that mean? Well, that means if there's a generic symmetry, that means that I should be able, on the heterotic side, to not ever build a bundle that is bigger than a certain rank that could break me past that point. So non-trivially, I've just got some information about which vector bundles could actually exist on those Calabi-Yau manifolds, because the complex structure of the fourfold is telling me what I can and can't do. I should mention that this was first studied by Rajesh, Berglund, and Meyer in the toric case back in the 90s. We've extended their results to non-toric geometry and done a more complete classification. And it turns out you can form tables of this type on this class eta, which is a piece of the C2, explaining for which H's, what are the conditions on eta that you have to have in order to realize a symmetry of that type. But in fact, we can go further. You can find that for many of these manifolds that have generic symmetries, in fact, if you try to start tuning the complex structure any further, the manifold goes too singular to admit a Calabi-Yau resolution. That means that you can't enhance the symmetry either. It means there is no possible way to supersymmetrically start breaking that vector bundle in a way that you can still preserve supersymmetry without something getting away from you. What this tells you is that there's constraints on which ways the symmetries can be enhanced. These are harder to put on one slide. There's a very rich texture. For example, there are many generic SU3s and SU2s which you can show can never be enhanced to SU5, for example. In many cases, it turns out that when I hand you a Calabi-Yau fourfold, there is exactly one symmetry that is generic, and it is impossible to enhance beyond that. So in these geometries, you can be pinned for that topology to exactly one 4-dimensional symmetry. Why is that interesting? Well, let's say you're in the business of trying to build models for string pheno, something that I've done recently on the heterotic side. If you're trying to build, say, heterotic string compactifications that look like the standard model, rather than scanning over 10 to the 12 different bundles on some manifold looking for one that looks like the standard model, if you have a filter of this type that tells you that only certain symmetries, and indeed we can do this for chiral matter as well in many cases, only certain types of chiral matter are possible, that's a very useful thing. So in my remaining 5 minutes, let me just say that what I just showed you was the first half of the story that I want to address. I'm using features of the Calabi-Yau fourfold to try and infer features of the 4D physics in an interesting way. But of course, to really do that, I also have to consider the G-flux. And in the previous discussion, I ignored G-flux up to this point. So a natural question for the topic of, for example, 4-dimensional symmetries that I want to be able to answer is, I was reading off the 4-dimensional symmetry from the Kadeira-Tate classification of the singular fibers. Does the gauge symmetry in 4 dimensions actually match what I would have read off from those singular fibers? Up until recently, the consensus would have been yes. In the M-theory limit, we would have said that abelian flux could not break non-abelian symmetries, so I wouldn't imagine an issue there. However, in the singular limit, F-theory can be much more subtle. It turns out that you can never have more symmetry than would have been indicated by the Kodaira and Weierstrass form, but with G-flux in the singular limit, you could have less. So the answer for this, of course, is very familiar from local F-theory model building, also from D-branes. It's already been discussed this week. This is the notion of T-branes, which appeared initially in work of Donaghy, Katz, and Sharp, and then was used very successfully in F-theory local model building due to Chakati, Cordova, Heckman, and Waffe, and also under the name of gluing data by Donaghy and Weinholm. So just as an example, very quickly, it is actually well known since the 90s, in a very beautiful example by Aspinwall and Donaghy, that this type of thing could get you in trouble in that you could read off the wrong symmetry from a Weierstrass model. And one very classic example is actually in 6 dimensions, taking the heterotic standard embedding in which the tangent bundle of the K3 produces an F-theory dual that looks entirely wrong. It looks like an E8 rather than an E7. So the question is, how is it that you can get this wrong? What is the extra degree of freedom in the singular limit that you need to understand? So I'm going to go rather quickly through this since I know everybody wants to get to lunch and the football. But let me just remind you what the notion of T-branes is and mention some really quick progress about actually understanding this in the global context. So as you've already heard about earlier this week, from the point of view of the world volume theory of a 7-brane, a T-brane is simply a Higgs field which describes the transverse motion of the 7-brane. In general, the Casimirs of such a Higgs field are related to complex structure moduli of the fourfold in ways that we've already seen this week. A T-brane is simply a way in which you have a non-trivial gauge field and Higgs field over the 7-brane, which you can hide from the complex structure. So this still breaks symmetry. You could still break E8 to E7, but it's no longer visible in something like the Weierstrass model, at least locally. So the question that Jonathan and Sheldon and I have attacked recently is how do you actually translate that local statement into something global? And how do you move between an M-theory description of G-flux towards such a local description? So the key new ingredient in this question was actually some work done by Diaconescu, Donaghy, and Pantev, not directly related to F-theory, but a beautiful piece of work building on earlier work by Donaghy and Markman, where they demonstrated that, in fact, the moduli space of the Hitchin system, that's this combination of a gauge field and a Higgs field here, where they showed the moduli space of Hitchin systems over a curve could be identified with the moduli, complex structure and intermediate Jacobian, of a non-compact Calabi-Yau threefold. More precisely, they were relating the integral systems variation of Hodge structure of the Hitchin system to that of a non-compact Calabi-Yau threefold. So with Heckman and Katz, what we've tried to find was a partial compactification of the DDP results in 6 dimensions. Specifically, what we found is that we found a way to consider one-parameter smoothings of a singular Calabi-Yau threefold, so here t equals 0 would be singular, in which you can actually track the degrees of freedom from a smooth geometry down to a singular limit, and actually discover that this local T-brane type data, the local Hitchin system, actually appears at the singular limit. And you can track this in a parametrically controlled way, basically providing a transition function to patch together the open and closed string descriptions of this geometry. Don't have time to get into the details here. The interesting thing is that in 6 dimensions, this seems to work very beautifully. You can actually track the Ramon-Ramon moduli, for example, in type 2a language of your threefold smoothly into the degrees of freedom of a Hitchin system in the singular limit. There is an open question, what happens for fourfolds, and this is something we're interested in looking at further. So since I'm out of time, let me just summarize what it is we've learned so far and where this is a first step, what we're heading towards. So what I've tried to argue for you is that n=1 heterotic F-theory geometries are a fruitful arena for classifying and enumerating a finite set of dual geometries. We actually hope to be able to enumerate literally all of them. We're working on systematically doing that. At present, what we're at is that we've developed an algorithm to systematically build all fourfolds with P1 bundle base B3 over a generalized Del Pezzo base B2. We explicitly constructed all heterotic F-theory dual pairs over toric bases. We've non-trivially checked topological consistency conditions and developed more sophisticated vanishing conditions for the moduli space of bundles on threefolds. To really finish this job, we require an understanding of G-flux in the singular limit, and we're making steps towards that in 6 dimensions through globalizing the notion of T-branes, using limiting mixed Hodge structures and emergent Hitchin systems. So this is a first step towards a more systematic study that I hope will take us towards the goal I described at the beginning. Thank you very much.